Hi, this is Mrs. Slater, and today we're going to talk about variation problems. First, you need to know what label that you're going to see over and over again. It's called the constant of variation, and it's a letter that represents a constant that will always happen, and we're going to call that letter K. And then direct variation, you're going to use a similar formula with the letter K, and it's y equals K times X, where K cannot equal 0. Otherwise, it would not be a problem to work on. Direct variation is when you have a like a cost of something, and then it has an effect on something else you do. For example, if you went on a trip, the cost of gas, if it goes up, then the trip cost, if you're trying to make budget, that's also going to go up. This is a direct variation because both of them are going to go up. Now let's talk about maybe a job. If you work less hours, then your pay is also going to go down. If I increase the amount of homework, what else increases? Your stress. So those are different ways to look at direct variation and what it means. Okay? Inverse variation is when things are opposite. So y equals k over x is going to represent it, where k, it's okay for k cannot be equal to 0. And examples of this are, let me fix this really quick. So examples, if the temperature goes up, ice, the size of ice would go down because it would melt. And then also, if I gave you a whole bunch of homework, if the amount increases, then your social life may decrease. So those are just different variations of inverse. Okay, and then as far as our examples are concerned, I'm just going to do a few of them straight from the book. You don't have to have your book. I'll explain what it is. But this is just a way to organize yourself. The first one, it says the directions. Find the constant of variation and the equation of variation, where y varies directly as x. So this is going to be direct, and so is anything from 1 through 8. So the first two that we're going to do are direct variation. Okay, and we're going to save that one for in class. So number 1, what is given is that y equals 24 and x equals 3. So the constant of variation formula is the first thing I want to use. And since it's direct, that's what we're going to be using. Okay, so let's go ahead and, sorry for the mess ups here. When you plug in the numbers, you get 24 equals k times 3, and if you divide both sides by 3, you end up with k equaling 8, and that is the constant of variation. So if you want to make an equation of variation, you would take the original formula and plug in the 8. So this is the equation of variation. Okay, so let's go on to the next page. Number 5 is still a direct variation, so I'm going to write that in right now. And the values given are y equals 15 and x equals 3. The equation we're going to have to use is y equals k times x. And after plugging everything in, 15 equals k times 3, so k is going to equal 5. Now if we're going to plug that back in, y would equal 5x. That's your constant of variation. Okay, now for inverse, which, nope, not yet. Direct is still number 8. You are given y equals 0.6 and x equals 0.4. I want you to solve for both of those boxes, and then we'll go over that in class tomorrow. Number 10. Now we are switching to inverse, so that would go in the second box. Number 9 is one you're doing for class, so I'm going to go ahead and just move that down here. 9 is also inverse, so you don't have to erase it. But what is given is that y equals 16 and x equals 4. And if you see that, let's see, that it's inverse, then you're going to use y equals k over x this time. Okay, and then k over x, we'd plug in the 16, you'd plug in the 4, and then multiply both sides by 4 to get 64 equals k. And because it's inverse, now we're going to use the equation of variation. So y equals the constant, which is 64 over x. Okay, now for the more inverse. So I want to do number 14 together. And you are given y equals 81 and x equals 1 over 9. And the constant of variation, that is a 1 over 9 by the way, the constant of variation is the inverse formula. And then when you plug it in, 81 would equal k over 1/9. And when you multiply both sides by 1/9, you end up getting 9. So your equation of variation would be y equals 9 over x. Okay, and now 16. This is when it gets more exciting because you actually have some story, like a real life story with it. Okay, this is for my science people out there. Hooke's law states that the distance, d, a spring is stretched by hanging an object varies directly. So they're talking about one of these springs. So they're saying that the distance, so that would be from here to here, the distance of this spring object varies directly as the weight of the object. So imagine like some hook and there's some weight that's being pulled on it. So the correlation between these is if the distance gets bigger, if the distance is bigger, what does that mean about the weight? That means that the weight must have gotten bigger as well. So that's the whole idea with Hooke's law. Now, let's go ahead and write some things in here. It's saying that the distance is 40 centimeters. It also says that the weight, or when it's 40 centimeters, the weight is 3 kilograms. Okay, and they say in the direction, you should look for it in the word problem, that it is direct. And to predict the distance when the weight is 5. So our prediction is when the weight is 5 kilograms, what is the distance? So that is our final goal. We want to make that prediction. All right, so let's find the equation of variation first. It's direct, so it's going to be y equals k times x. Now, this one, we don't have y and x, we have d and w. So when you look at your equation, it says that the distance varies directly. So distance varies directly as the weight. So you would write it as you see it in the sentence. And when I plug in information, 40 and then k times 3, k is going to equal 40 over 3. And we're just going to keep it that way, keep it in exact form. So then your equation of variation is 40 over 3 times w. And I messed up on the y. I want to keep it with d. It's just a lot easier to plug in our prediction, because now I know w is going to go and replace the w, and now I'll be able to find the distance. Multiply that together, so distance equals 200 over 3. Which is approximately 66.6 repeating centimeters. So as the weight goes up, the distance is going to go up as well. Number 22 says the weight of an object on the moon varies directly. So there's our key for direct. I'm going to go ahead and write that in there. As the weight on Earth. A person who weighs 95 kilograms on Earth weighs 15.2 kilograms on the moon. How much would a 105 kilogram person weigh on the moon? Okay, so if it's direct variation, we're going to use this formula, y equals k times x, and the object on the moon varies directly, so we are going to call the weight is going to be m, because that's on the moon, and the weight on Earth is going to be e. So that's the moon, and this is the Earth. So that will help when we do the work. So a person who weighs 95, this is Earth, 95 kilograms, weighs 15.2, and then 15.2 kilograms on the moon. And then if you read it, it says moon varies directly. So moon equals k times e. Moon varies directly as the weight on the Earth. So we're going to plug this information in. 15.2 equals k times 95. And then if you do the math, k ends up equaling 0.16. So the equation that we're going to need is m equals 1.16 times e. Okay, now the prediction, it's asking you how much would a 105 kilogram person weigh on the moon. So then you would use this constant of variation equation, because on Earth you've got a 105 kilogram person. So it would be m equals 0.16 times 105. And after multiplying that together, you end up with the person on the moon would be 16.8 kilograms. Okay, and as you've been able to tell from, I'm a little frustrated with the video today, so I'm going to go ahead and stop there, and then we will continue the rest in class. All the multiples of 3 are going to be your assignment. If you would like to start ahead, you may do so as well. See ya!